So yeah, we in the first session we learned about the different forces that acts on a object when it's in air. Like there are basically four forces: thrust, drag, lift, and weight. We define all these forces, and we also give the explanation that how lift and drag are generated using different theories. We quantitatively define these forces using formula, and we also explain the nomenclature used for the airfoil and how lift coefficient changes with the angle of attack. Yeah. So do you guys have any doubt regarding the last session? Okay, so if there are no doubts, we will starting with session 2. So session 2 is about various aerodynamics parameter and installation of Ansys workbench. So what are these aerodynamic parameters? Aerodynamics parameters are different numbers that we use to define the flow of object in air. And we have also learned few of these parameters in previous session, like lift coefficient and drag coefficient. So what is lift coefficient? A lift coefficient is a dimensionless coefficient that relates the lift generated by a lifting body to the fluid density around the body, fluid velocity, and an associated reference area. And the formula is here. This is the lift coefficient, and it is given by the ratio of the lift force to the product of area and pressure density. This is pressure term, half rho v square. And yeah, similarly, the drag coefficient is similarly defined. And here we have given drag coefficient value for simple geometries. For sphere, it is 0.47. For half sphere, it is 0.42. And for cone, it is 0.50. A point to be noted here is that all these drag coefficients are for zero angle of attack. And here is a factor, like what is Karman line? Karman line is a boundary that separates the Earth atmosphere and outer space. And it is usually defined as 100 kilometers from Earth's mean sea level. That's just a fact. And here is a plot between log CD versus log RE, where CD is drag coefficient and log R is NRE, Reynolds number. And a doubt you guys will be having is why are we plotting this log CD versus log RE, not CD versus RE? So that's because when we plot CD versus RE, we get a very non-linear curve that is very difficult to explain. But when we draw this graph on a log-log graph, we get a straight line in a particular region that is known as Stokes Law region. And you guys would be already be knowing what is Stokes Law. That is given by force is equal to 6 pi eta RV. So when we plot log CT versus log RE, we get a straight line in a Stokes Law region. Yeah, so and that Stokes Law is only valid till the log RE is equal to 0.3. And this graph is only valid for a spherical body moving through air. And here is the Reynolds number ranges for single particle drag coefficient correlation. Like if we have to find the drag coefficient value for different kinds of, for in the different region of RE. So yeah, any doubt regarding these two slides? Okay, there are no doubts. We'll be going ahead. Airfoil terminology, how we nomenclature the airfoil. So this is a basic airfoil cross-sectional area of an object. This is chord line that joins the leading edge and trailing edge. This is angle of attack, the angle between chord line and relative wind direction. This is total aerodynamic force, and lift force is the perpendicular component, and drag is the horizontal component in opposite direction of motion. So like we will be starting with center of pressure. The center of pressure is a point on the chordwise location. It is located on chordwise, about which the pitching moment is momentarily zero. It is the point where the resulting force vector due to the pressure distribution and shear stress acts through this point. Aerodynamic moment is zero. So what is written here is that this is the total resultant force, and this is the center of pressure. But like if we take at if we take moment at any other point, like for here, like there will be a this force will be acting on this point and also a moment that is given by F into this distance. And similarly, if we take moment here, we will be getting this force and the torque moment also. That is given by F into this distance. But when we take the moment here, we don't get any moment. Only resultant force acts at this point. So that is what is written. The resulting force vector due to the pressure distribution in shear stress act through this point. Aerodynamic moment is zero. And what is stalling? Stalling is the reduction in lift coefficient generated by a foil as the angle of attack increases. It varies with NRE, fluid, and foil. So what is stalling? I have included the graph. So yeah, this is the graph for stalling that explains stalling. This is lift coefficient versus angle of attack. When as we increase angle of attack, the lift coefficient increases, but at a certain angle, it starts to decrease. And this is known as stall angle. And this phenomenon is known as stalling. And this happens because uh, when we as the angle of attack increases, the boundary layer starts to separate, and but there will be a diagram. Yeah. Uh, yeah. So as the angle increases, firstly the boundary layers are closely, they are together, they are not separated. Yeah, like you can see here, the boundary layers are close together, they are not separated. But as we increase angle, the boundary layer starts to separate, and there is a formation of region, like suction region that has the presence of turbulent eddies. So that increases the drag, so lift coefficient decreases. So that is what is reason stalling. Reduction is lift coefficient generated by a foil as angle of attack increases. Coming to the aerodynamic center, it is the chordwise location about which the moment is independent of the lift coefficient and angle of attack. Uh, like uh, yeah, like if we consider an airfoil at zero angle of attack, alpha is equals to zero, and this is our total resultant force. And if we consider the moment from the leading edge, we will moment will be given by m is equals to r into d. And as angle of attack increases to something value x, the moment will this total resultant force will change to r dash, and this distance will also change to d dash. So we can see like as the angle of attack increases, the moment also changes. But there is a certain position on the chord line such that uh, dm versus d alpha is zero. That moment doesn't vary with angle of attack. So that and we define that point as aerodynamic center. It is the chordwise location about which the moment is independent of the lift coefficient and angle of attack. And like if we non-dimensionalize this term, like we will get This dm by d alpha can also be written as dcm by dcl, whereas cm is the pitching moment coefficient and cl is the lifting coefficient. So like they are independent. So that's how we define aerodynamic center. And pitching moment. Pitching moment is nothing but just aerodynamic moment. It is the moment produced when aerodynamic forces are considered to be acting on the aerodynamic center of the wing. It is given by the resultant force versus product of resultant force and distance. I doubt you guys will be having like, wow, why are there two centers? But like in center of pressure, as we increase angle of attack, like yeah, as we increase angle of attack, the center of pressure, the position of center of pressure varies. Like as alpha increases, center of pressure like comes closer to the leading edge. Like if for 0 angle of attack, it is here. For like 20 angle of attack, it will come closer to the leading edge. So like we cannot use the center of pressure for the numerical and calculations because it changes. But aerodynamic center is like independent of the angle of attack. Dm by d alpha is 0, and that's why that that is much more helpful. So any doubts regarding these four terminologies terms? Uh, like you guys can ask doubt. Okay, fine. If there is no more doubts, we will go ahead. Like this is NACA 4-digit series. How we in industrial, how we define the, like it's the nomenclature of the airfoil. Yeah. So like NACA is the full form of NACA is National Advisory Committee for Aeronautics. It is a government body in USA that defines the naming of the airfoil. And for like there are many ways that how we can define this airfoil. Like there is 3-digit series, 4-digit series, 5-digit series, but 4-digit series is the most prevalent and popular and also easy. So the basic structure of the 4-digit series NACA MPTT. For example, NACA 2412. What is MPTT? Like you guys would be you guys will be knowing the structure of the airfoil by now. M is equal to maximum camber as percentage of the chord. Camber is a curvilinear line that is equidistant from the upper surface and lower surface, and camber line is a straight line. And M is the maximum camber as percentage of chord. Like in this diagram, the chord line is 1 meter and this camber is 0.02 meter. It is maximum camber, so it is like 2%. So M will be our 2, NACA 2. P is distance of maximum camber from the airfoil leading edge in tenths of the chord. In tenths of the chord, because it's 1 meter, it will be in 0.4. This is P is equals to 4, so it will be like 0.4 meter away from the leading edge. And this TT, this is the maximum thickness as percentage of the chord. So this is 12, so it will be 12% of 1 meter. So it will be like 0.12 meter. So the maximum thickness will be 0.12 meter. So like if we are given this number, 4-digit number, we can draw the graph of the airfoil. What is Mach number? Mach number is a very useful term that is used in aerodynamics and aeronautics very frequently, and it is defined as the ratio of object speed to the speed of sound. Like for subsonic aircraft, like general airlines, it is below the speed of sound. Object speed is less than speed of sound, so they are subsonic. So Mach is 1. Mach number is less than 1.0. And when the object speed is equals to speed of sound, they are known as transonic. supersonic that travels above the speed of sound, and hypersonic that travel much faster than the speed of sound. 5 is not like digit term, like a lot, a lot faster than the speed of sound. So any doubts regarding NACA 4-digit series and Mach number? Okay, we'll be going ahead. What are flaps and slides? If you guys have ever been in airline, you guys would be seeing these flaps and slides in the wing of the aircraft. Like this is a basic non-immovable structure that doesn't move, but there are slats and flaps that are located at the front and the back end of the aircraft wing that is used to generate high lift and also drag sometimes. Flaps and slats are high lift devices that are used during landing and takeoff. Because during landing and takeoff, they are very different kind of scenario, and we need high lift and high drag at those conditions. Flaps are located at the trailing edge at the back end of the airfoil, and slats are located on the leading edge. They serve the main purpose. They like increase or decrease the camber of the airfoil. This is cruise configuration main wing that doesn't move. Slats, flaps. Yeah, this is like a mechanism so that they can move. As like from common sense, we can get that during takeoff, we need high lift because we have to like get away from the ground. So we need a high lift. So during takeoff, flaps are extended, resulting in increased camber. So like in resting position, the camber is very straight, but like when they are extended, slats are extended, sorry, flaps, the camber increases, it becomes like this. It results in increased camber, smaller angle of attack, and high lift. High lift is because due to the higher angle of attack, but this angle of attack must be less than stalling. And during cruising is like the period between takeoff and landing. The flaps are retracted because the high lift is no longer required. Because during cruising, the airline stays at a certain distance from the ground. It doesn't go up and down. So during these flaps are extended, there's a very also high drag. But so to reduce the fuel consumption, these flaps are retracted during cruising. So it reduces lift and drag simultaneously. So that's the basic work mechanism behind flaps and slats. This is the basic structure of an aircraft. And you don't need to remember like how these work, but you guys can remember the terms. This is leading edge devices. This is spoilers. This is vertical stabilizer. This thing. This is rudder, elevator, horizontal stabilizer. These are flaps that we just learned. What are they? These are wings, wingtip devices. Yeah. So the vertical things are known as vertical stabilizer with rudders. Are these things can move, and these are horizontal stabilizer with elevator. Elevator can also move. Horizontal stabilizer maintains the moment in maintains the roll axis so that it doesn't move the aircraft doesn't get turned behind between the cruising, so it maintains the normal axis of the aircraft so that it doesn't get turned away. These are different axis terms that are used in aircraft. The axis in the direction of motion is roll axis, and the perpendicular downward to the ground is known as yaw axis, and the other axis known as pitch axis. So all these terms you guys have to remember. So this is the basic problem. Determine the drag coefficient of a 75 kg skydriver with a projected area of 0.33 meter square and a terminal velocity of 60 meter per second. By how much the skydiver need to reduce her project area so as to double her terminal velocity? During terminal velocity, we know from our class 11th understanding, the downward force is equal to the upward force. So R is equal to W. Drag force is so drag coefficient is 1.22. And the second part of the question is by how much would the skydiver need to reduce her project area so as to double her terminal velocity? So we again use this equation that we got, and we remove the terminal velocity term to the left side of the equation, and we get a relation between Vt versus A. Like Vt is inversely proportional to the square root of the projected area. So like, what's the question? To double her terminal velocity. So like, if we have to double the terminal velocity, we would have to reduce the projected area by 1/4. And so you guys, so that's why the skydivers change their position to get increased velocity. So when they like come down in a vertical position, their terminal velocity increase and they can come at a faster velocity. This is a takeaway home problem like which you guys can solve. And if you have doubt regarding this, you can ask on Teams. The solution will for this problem would be 22.7 horsepower. So you guys can check your understanding. So try to solve this problem. If you don't get it, it's fine. Ask us. We are here to help you guys. Now coming to the second part of this session, installation of Ansys. So how we install Ansys. So we will search on the Google Ansys. We go to the first link, students and academic, the student software. Mm, this the Ansys student. For our SMP, you guys would be downloading this one, download an Ansys student 2022 R1. So when you click this, it will start downloading. You guys can download anytime using the NITK Wi-Fi. So like when this is done, these are installation steps. The downloaded file will be in the zip format. You unzip, you like accept all the files and run the setup.exe file as administrator. Accept all the terms and condition. And like any software, you know how to install. The Ansys software is now installed. Congratulations. The requirement for this Ansys software would be 4 GB RAM and 25 GB of hard disk space. Yeah, so you guys will be getting screen like this with terms and condition. Agree and click next. Yeah, so it will start installing in your workspace. And when will it get done, it will be available in like this. So it will show you something like this when you start. Let it finish. We will go ahead. So that that's it for week one, both sessions. So we learned about the basics of aerodynamics, various aerodynamics parameters, and installation of Ansys software that we will be using to simulate the aerodynamics of F1 airfoil. And this is a basic prequel like what we'll be learning in the coming session in week 2 and week 3, aerodynamics of F1 car. It follows the same principle as common aircraft that we just learned, how the lift and jacks are generated, what's the equations. Like air below is squeezed, and so by conservation of momentum, the air speeds up, creating low pressure region. In the aircraft airfoil, we were seeing that the lower pressure region is at the upper surface, but in the airfoil, this is available. This is at the lower surface. The low pressure region at the below, and the high pressure region is at above position. So this airfoil, this airfoil tries to push the F1 cast downward because the rear wing pushes air up. Hence, airfoil is being pushed towards ground by air. That's by Newton's law. This downward force pushes car into the track to create more grip, because these F1 cars drives at a very high velocity. So to generate high grip, this downward force is necessary. And so this is the basic airfoil. It is like the inverted shape of the common airfoil of the aircraft. So yeah, you guys will be learning this concept in more depth in the coming session. So that was it for the week one. I hope you guys understand. If you have any doubt, contact us, any of the mentors. We will be happy to help you guys. So that's how the answers workbench is. We can create a new project. Yeah.
Okay,